Hi everyone, my name is Rashmeet Kaur Nair, and today I'll be presenting our work on autonomous option invention for continual hierarchical reinforcement learning and planning. In this work, we consider a standard reinforcement learning setting where the transition and reward functions are not known. And so existing deep RL methods have made significant advances in RL. And so we evaluated the scalability of popular deep RL methods such as PPO on an office world domain with sparse rewards. And we observed that as we increase the complexity of the problems, the size of the problems, the performance of PPO degrades very quickly on simple domains like office world. And so we also tried this on other popular deep RL methods such as A2C, DQN, and observed a similar trend. So I focus on this special case of RL called continual RL, where the agent has to solve a stream of tasks one after the other. The transition and reward functions are non-stationary, and the initial and goal states keep changing across the tasks. So for example, here, I'm showing here an illustration for the taxi domain where the pickup locations and the drop-off locations are changing. So the taxi agent needs to pick up a passenger at a certain location and then drop them off at the destination. But these drop-off and pickup locations can vary across different tasks. So this is an example of a continual RL problem. And so our one way to address the sample inefficiency that I talked about earlier is to learn options where we are breaking down a problem into subproblems. Anita here in the previous talk already established and defined what an options framework is. Our if we learn options, then that will help us to easily scale because we can plan over these options. But if we can learn these options and also transfer these options across tasks, then that will also help us to address the problem of continual RL. And that is the objective of this work. So our goal is to invent options with three desired properties. We want to invent options that can be composed together one after the other. So the effective horizon of the problem is smaller. We want to invent options that minimizes the need for relearning. So the amount of experience that is required should be reduced. And we want to invent options that are mutually independent from each other. So one option should not interfere with other options. Now, we had some prior work where we were able to show that we can learn state abstractions autonomously on the fly during Q learning. We call these abstractions as conditional abstraction trees. So they're formally represented in the form of a tree, but I'm just showing an illustration here. And in this, we can see that the abstraction on the left is for when the passenger is at the pickup location. So it's showing an abstraction which is more granular towards the pickup location of the passenger. And the abstraction on the right shows more granularity towards the drop-off location. So that's an abstraction when the passenger has been picked up by the taxi. And you can see that in parts of the abstract state space, we need less granularity in the policy, but there are parts of the abstract state space where we need specific decisions to be made. So the key idea is that conditional abstractions can automatically switch depending upon the state. And our intuition for option invention here in this work is that if we can identify, if we can detect significant changes in the abstraction, then we can use that to invent an option. So for example, here, since the abstraction on the left, when the passenger is at the pickup location, it looks very different from the abstraction when the passenger is in the taxi. That gives us a cue for inventing an option so we can invent a pickup option there. Also, I'd like to point out that this would fall into a model learning space, as Matthew was describing, because we're learning these abstractions and then using them. So we don't have a full model. We're learning sort of a partial model, which can be represented in the form of abstractions. So our overall approach here is to combine planning and learning. And so we start with a task where we first learn state abstractions autonomously in the form of a CAT, a conditional abstraction tree, and we learn a policy for that particular task. And the idea is to use these state abstractions, which are autonomously generated, to invent options. And when a new task comes in the continual RL setting, we can then use the planner to compute a plan over the existing options that we have learned. For each of the option in the plan, we can fine tune the abstractions and the policy for the option if needed in the plan. So we continue this process as the new tasks keep coming. That's the overall idea of combining planning with learning. And here's just an example of auto-invented options in the taxi domain. So we have the taxi at the start location. So the option would be to navigate to the pickup location. There's another option where the taxi is at the passenger location. So an option was invented which would pick up the passenger. Here, I'm just showing how once we have a set of options that we've learned, how we can compute a plan over the options. And so we've also proposed a novel planner which would compose the options, but also bridge gaps between options. So we can define new option that bridges the gap between sequences of options, and then later on learn a policy and abstractions for those empty options. So here are some of the results by this algorithm chip. We compared with I'm just highlighting one domain here, but I'll show rest of the results as well. So here, all the domains had continuous state spaces. We randomly generated 20 tasks, one after the other, for the agent to solve in a continual RL setting. So the tasks were not known beforehand. And there was a fixed budget allotted to each approach to solve a task. So, and we compared our approach with a variety of baselines, approaches that learn state abstractions, or approaches that focus on inventing options, and deep RL methods that learn some inherent latent form of abstractions. And so Chirp, as you can see, performed significantly well. I'll also like to point that these domains are long horizon sparse rewards, which are complex. Here are some of the results for all the other domains that we tried. So as a summary, the chirp algorithm in this work is autonomously able to invent options using auto-generated state abstractions, and we showed that these learned abstractions help improve the sample efficiency in a continual RL setting. I have the QR code here, so please feel free to read more details about the paper, and I'm open to questions.
We have time for one quick question. People with the spotlight talks, please line up. One quick question.
So thank you. So am I right to understand that you're trying to learn symbolic actions?
So their initiation and terminations are symbolic. Yes, because like they're interpretable. So they're in terms of variables and value ranges. So we're learning state abstractions and then learning options. So the options are represented symbolically.
Right. So you can just use classical planners on top of that, for instance.
Yeah.
So I was wondering whether you are usually learning things like move, pick, drop, or is it other stuff that you have observed?
So the focus here is on learning semantically well-defined options. So the idea is that because these problems are long horizon, we want to be able to learn options that does something like pick or something like navigate to a specific location when for solving a long horizon problem. But we've also kept the framework general. So if we want to invent more options like navigate to this location, then that location. So like if we want to break down the already learned semantically well-defined options, then we can also do that.
Thank you.
Let's thank our speaker.